Hello, and welcome to the video lecture for topic 11, optical activity, stereoisomers, RNS, and Fischer projections. Now, I'd like to start off by saying that I feel that both your textbook and the POGIL worksheet do a really great job of covering the information that you need to know on optical activity. So I'm not going to be discussing that topic or that point here in this video lecture, and instead I'm going to focus on stereoisomers, RNS assignments, and Fischer projections a little bit at the end. So the issue of stereoisomers can be divided into two considerations: relative stereochemistry versus absolute configuration. And in topic 10, we began to examine relative stereochemistry, specifically in terms of cis-trans isomers when we have substituted cycloalkanes. And so these definitions of cis and trans, that just describes the relative configuration of these substituents around the rings, right? And so we have the two stereoisomers, cis and trans. However, we like to be a lot more precise in organic chemistry than just having these relative assignments, and we want to be able to know what we call the absolute configuration of a stereocenter. So to review, from the end of topic 10, we talked about how we could have a carbon atom where we attached 4 different substituents to it. So here I'm going to just draw a carbon atom, and I'm going to put 4 halogens around it, right? A fluorine, an iodine, bromine, and chlorine. And how we could draw a non-superimposable mirror image of this same carbon atom with 4 different substituents. So here's my non-superimposable mirror image, right, defined by this mirror plane. So we could say that just based on our understanding, right, that we developed in topic 10, we can say that these two carbons are enantiomers of each other. They differ in their configuration, right? They are non-superimposable mirror images. But we have actually a way to convey exactly what configuration these 4 different substituents on a carbon atom have. And that's what's known as R and S notation. So to determine the absolute configuration of a chiral carbon, whether it's R or whether it's S, we do something very similar to what we did with assigning EZ nomenclature to alkenes, in that we look at each of these substituents, each of these 4 different substituents individually, and we assign them a priority rank based on the Kohn-Ingold-Prelog or CIP rules. And so if I look at this carbon atom that I have here, what I'm going to see is that the substituent with the highest atomic number, iodine, is going to take priority 1 in both instances. Moving, down in terms of priority, bromine is the next largest. It would take priority 2. Chlorine would follow at priority 3. And then finally, fluorine has the lowest priority since it has the lowest atomic number. Now, here's where we differ from assigning alkene stereochemistry. Once we've assigned priorities to each of the 4 substituents on our carbon atom, we, in our mind, place the lowest priority substituent, the substituent priority 4, on a wedge behind that carbon, hidden behind that carbon atom. So luckily here, I've kind of pre-programmed this example that my lowest priority substituent is already on that wedge. So that task has been completed. From there, we follow around our substituents from 1 to 2, and then from 2 to 3, and we see whether these arrows lead us in a clockwise motion, as we have here on this side, and we would assign an R stereochemistry, versus a counterclockwise for this enantiomer, which would lead us to an S stereochemistry. And so this process can be done for any chiral carbon atom. So that's any carbon atom that has 4 unique substituents on it. This is a relatively simple and straightforward example, but let's look at something that's a little bit more complex. So here now, I'm going to draw a new chiral carbon and put 4 different substituents on it. a methyl group, a hydrogen, an aldehyde, and a chlorine. And now the aldehyde is coming out of the board towards you, and the chlorine is coming behind the board towards me. I can repeat my priority assignments using CIP rules. So here now I would have my hydrogen is lowest priority, priority 4. From there I know my chlorine is the atom directly attached to my carbon that has the highest atomic number. So my chlorine is going to have priority 1. And then distinguishing for 2 and 3 between this methyl group and this aldehyde, right? If you follow your CIP rules into shell 2, you'll see that the aldehyde has higher priority than the methyl, giving it 2 and placing our methyl 3. Now, unlike our previous example right here, right, our lowest priority group is not on that hash pointing away or pointing behind the board, which is where we need to get it. So we have to rotate this entire molecule three-dimensionally in space and then redraw it such that this hydrogen atom is now on the hash. I've already gone through and done this on my own, but you should recognize that this process for some folks is going to be a little bit challenging just to do in our mind's eye, and so a model kit is really, really useful at this stage. Build a model of your carbon atom and then rotate it so that you get that lowest priority group pointing back. So once you've done that rotation, we'll see that while we haven't swapped any positions of the group, we've just rotated the molecule. To get our hydrogen on that hash, we put our chlorine and methyl group in plane with the chiral carbon, and our aldehyde would remain on the wedge, right? So now we preserve those priorities from before, 1, 2, 3, and 4. Our hydrogen is still pointing back for us, our hydrogen is now pointing back for us, and we can do our 1 to 2 to 3 arrows around our chiral carbon. We see here that our priority decreases, moving counterclockwise, and we can set this as a S stereocenter. So we've looked at situations that are applicable to a open chain or acyclic alkane, right, and a chiral carbon within an acyclic alkane. But how do we then do this process? How do we determine the absolute configuration of a stereocenter of a chiral carbon in a cycloalkane? So we're going to take a look at that here next. So the process for determining the chirality of a stereogenic carbon in a cycloalkane differs very slightly whether we're working with a ring with an odd number of carbons versus a ring with an even number of carbons. And we're going to take a look at examples that cover both of those. So to start out, let's look at an odd numbered ring. So this would be your cyclopropanes. Here I'm going to use cyclopentane. But this system would also apply for a cycloheptane, a 3, 5, or 7-membered ring. This would work. So I'm going to create a stereogenic carbon right here, and I'm going to put a methyl group on my wedge and a hydrogen on my hash. Now, to make this example really work, I'm going to go ahead and put a ketone on this ring as well. So now I want to determine the absolute configuration of this chiral carbon. And really I have 2 substituents that are easy to tell, but how do I differentiate the ring, right, into 2 different substituents so that I have 4 substituents to compare with? And the way we do that is by dividing this ring in half. So we find, for our odd numbered rings, right, 3, 5, and 7, we find the bond that is opposite of our chiral carbon, which would be this bond here, and we break that ring bond in half. We can now redraw our chiral carbon as an acyclic alkane. We maintain our methyl group on the wedge. We maintain our hydrogen on a hash. But now, for this side of the ring that contains the ketone, we would put our CH2 group, and then we would have a carbon with a carbonyl. Remember, we broke that bond there. For the other side of the ring, we have our CH2 group, and then we have another CH2 group. So now I have my stereogenic carbon displayed in a fashion with 4 unique groups around that carbon atom. And I can once again assign priorities. Our hydrogen, priority 4. If we then go through and look at our 3 remaining substituents, we'll find that the one containing our ketone, or our carbonyl functionality, has priority 1. The group that's just 2 CH2s, that's the pseudo-ethyl group that we have here, would be priority 2. And finally, our methyl group on the wedge is priority 3. Conveniently, we already have our hydrogen atom pointing back. And so what we see here now is that if we go from 1 to 2 to 3, we are moving in a clockwise direction, and we can assign the absolute configuration of that stereocenter as being R. Let's take a look at what happens when we're working with a 6-membered ring. So for our 6-membered ring, and this system, this method that I'm going to use applies for any ring that has an even number of carbons. So that's a cyclobutane, cyclohexane, cyclooctane. As long as it's got an even number of carbons, the system will work. And this time, though, I'm going to put my methyl group on a hash and my hydrogen on a wedge. And I'm going to use once again, I'm going to use a ketone to differentiate the 2 sides of the ring. So here, with an even numbered ring, there's no bond opposite of my chiral carbon, but in fact there's just another carbon on the other side. And so I'm going to go ahead and split that carbon in half, and that's where I'm going to break my ring. So now to redraw that chiral carbon, I have my methyl group on a hash, I have my hydrogen on a wedge. For this side of the ring, I have a CH2 group, a carbonyl, and then essentially I'm going to, instead of calling this a CH2 or a CH or trying to figure out what it is, I'm going to put a placeholder for it. So here's my CH2 group, here's my carbonyl, and then for this group that I broke in half, this ring carbon and its attached hydrogens that I broke in half, I'm going to put a placeholder Z. The reason I'm going to do that is because I'm going to use that same placeholder for the other side of the ring. So there's my first CH2 group, there's my second CH2 group, and there's my placeholder Z. Since both of these chains are attached to that group we broke, that group is not going to affect their priority ranking with CIP rules. And so we don't need to take it into consideration, and we can just put a placeholder there, Z, 2 things that are equivalent on each end of that chain. We can then go about assigning priorities to each of the groups on this chiral carbon now. Once again, we'll see that we have hydrogen is priority 4. Our methyl group this time will be priority 3. Our ring side that only had methylenes in it will take priority 2. And our ring side that had our ketone in it, or our carbonyl in it, will take priority 1. Notice here that my hydrogen is on a wedge. I need to put it on a hash, and so I'm going to reorient this molecule by flipping it over. And so that would look like this. I move my carbonyl Z group to this side. That's going to flip hash and wedge for my methyl and hydrogen. So now my methyl's on the wedge, and my hydrogen's on the hash, and my ring side that only had methylenes is going to be over here. And again with my placeholder Z. So my priorities are still 1, 2, 3, and 4. Now, going around my substituents from highest to lowest, going 1 to 2, and 2 to 3, I am now moving in a counterclockwise direction. And so I can assign the stereochemistry of this chiral center. Its absolute configuration is S. All right, so one of the trickiest things, if you've been stuck with me this far, is remembering to do that reorientation and put your number 4 priority group onto a hash before you assign absolute configuration. Keep in mind that lowest priority group isn't always a hydrogen. In our very first examples that we saw, that low priority group was a fluorine, and really it's just whatever group has the lowest priority based on CIP ranking. So far, though, in this video lecture, we've only considered situations where we have one chiral carbon in a molecule. This is a very rare case. We usually have 2 or more. So I want to take a look now and see what goes on when we have some of the relationships that are going to occur, when we have a molecule that has 2 or more chiral centers. Okay, so for molecules that have more than one chiral center. Let's start off by just drawing a generic organic molecule that could potentially have more than one chiral center. Right? So I have this ketone, it's got a methyl group and a chlorine, and so I can potentially have a chiral center at this carbon, and I can potentially have a chiral center at that carbon. Since I have 2 stereocenters, and each stereocenter can be either R or S, I have 2 to the power 2 total possible stereoisomers. So there are 4 different ways that this molecule could potentially be configured. And I'm going to go ahead and draw all of those out for you now and label the individual stereocenters. So we could have one where our methyl group is on a hash and our chlorine is also on a hash, and we would find, after assigning chirality or assigning absolute configuration, that both stereocenters are R. We could also have, I'll make a little space here, we could also have a situation where our methyl group is on a hash and our chlorine is on a wedge. And if we assign our stereochemistry, we can see that we held the methyl group stereocenter, we held constant, it stays R. However, we've swapped the stereochemistry at our chlorine stereocenter, so it has now become S. I can do the opposite of that, where I keep my chlorine on a hash, and this time I put my methyl group on a wedge, which would give me S at this stereocenter and R at that stereocenter. And the fourth option would be my SS enantiomer, SS configuration, where my methyl group is on a wedge and my chlorine is on a wedge. And here now we have S and S. So starting from our RR configuration, sometimes we change one stereocenter and sometimes we change both stereocenters. So how then can we describe the relationship between these 4 different configurations? Well, if I change only one stereocenter, for example here I'm changing this stereocenter from R to being S, these 2 different configurations have a specific name known as diastereomers. And that term can be applied anytime we have 2 relatively identical organic compounds where there are more than two stereocenters and only one configuration is changed. So diastereomers, one change and one the same. Right? So I have changed at least one of my stereocenters, but I have kept at least one of my stereocenters constant. And if we go here now, we can see that that's true all the way around this little diagram. Between these two, R changed to S, R stayed R, these are diastereomers. Between these two, S stays S, but R changes to S, these are also diastereomers. And finally here, S stays S, but S turns into R, these are also diastereomers. What about the relationships going across the ring, right? So we've compared this RR conformation to the RS conformation and to the SR conformation, but we didn't compare it to the SS conformation. So going diagonally now, we have changed both stereocenters, right? We took RR, we made them SS. These are a different kind of enantiomers. But what it has in common with our previous discussion of enantiomers is that two molecules are enantiomers if all stereocenters change. This is true even if I have more than two stereocenters in a molecule. Every R stereocenter in one depiction or in one configuration must become S in the second, and every S configuration in the first conformation must be, or in the first configuration, must become an R configuration in the second molecule. And so we see here, going from SR to RS, we also have a pair of enantiomers. Okay, so remember diastereomers, you have at least two chiral centers, one of them changes between the two configurations. Enantiomers, doesn't matter how many chiral centers, one or more, but the two different molecules, all the configurations at stereocenters change. So, couple more things, right? Next thing I want to talk to you about is going to be a unique situation where we have a molecule that has chiral centers in it, but is overall achiral. So if I have a compound that contains chiral centers, one or more in it, but somewhere in that molecule I can define a mirror plane, there's a very special name for it, and it's called a meso compound. This is a molecule with a chiral center, or I should say at least one, but also has a mirror plane. Or sometimes called a plane of symmetry. So let's take a look at an example. So if I take this cyclohexane, and specifically 1,2-dimethylcyclohexane, I see that I can have up to two chiral centers in it. And so I can have up to 4 configurational stereoisomers. And let's draw those out. So I can have wedge and wedge. I can have hash and wedge. I can have wedge and hash. And finally, I can have hash and hash. So 4 different configurational stereoisomers, right? What we're going to see, though, is that in 2 of these, we actually have a mirror plane of symmetry dividing that molecule in half. Now, my examples here, I'm going across a ring, right, through a couple of bonds, but there's lots of different ways that that mirror plane of symmetry can exist, depending on the specific molecule. It doesn't necessarily have to cut the molecule in half through bonds. It could slice through the molecule through a plane containing several atoms. It can go diagonally. There's lots of different ways. So you really have to look for that mirror plane of symmetry, right? And consider all the different ways that you could cut this molecule and create two mirror images out of it. But we see here, for our example of 1,2-dimethylcyclohexane, that both of our cis conformations or configurations, our up-up cis and our down-down cis, have this mirror plane of symmetry. And so we have a molecule with at least one chiral center that also has a mirror plane of symmetry. These are meso, is how we define their stereochemistry. They are meso compounds. And these two configurations are actually achiral. Right? So while they have chiral centers, the overall molecule is achiral. It will not rotate plane polarized light, right? So meso are achiral overall. Okay? They still contain chiral centers. Now the POGIL worksheet and in Sorrel goes through some other examples that show you meso compounds. Sometimes you have something acyclic where you need to do some bond rotations, right? You need to put it into the right conformation, right? The right conformer for us to be able to do that, but to find that mirror plane. But you will never change configuration in order to find that mirror plane. All right. The last thing I'd like to talk to you about in this video lecture is Fischer projections and how to interpret them. And so we'll take a little pause here and get into that next. So Fischer projections are just one more way that we can depict a molecule, right? An organic compound. These are named after Emil Fischer, who was a very famous carbohydrate chemistry and developed this system of drawing molecules. And Fischer projections are most common when we work with carbohydrates. They're the most common way that we draw carbohydrates. Now, we're not going to get into carbohydrates until Chem 202, so we've got a little while before we start using them regularly, but you do need to understand how to interpret a Fischer projection and how to derive stereochemical absolute configuration information from a Fischer projection. So let's take a carbon atom, right, and let's put 4 unique groups around it. Here now I'm going to use A, B, C, and D. Right? I can imagine cutting this molecule in half or dividing this representation with a line that cuts through the carbon atom like this, which places 2 of the substituents above the carbon atom and 2 below. It's a little bit easier for us to see it if I draw it this way. There's my carbon atom, here's B and A, and then here would be C and D, and here's that plane that divides my carbon atom above and below. If I imagine myself looking down at this molecule, so taking this type of perspective view, we would see that a shadow, right, if I shined a light down on it, the shadow it would cast would put a carbon atom at the center, would put a carbon atom at the center, and then I would have A off to one side, B to the other side, D above, and my C group below. So anything above this line that we use to cut the carbon in half goes on a horizontal line, and anything that's below goes on a vertical line. The other way that I could think of this is that anything that is above, right, would go on a wedge, and anything that is below goes on a hash. And my wedges go horizontally and my hashes go vertically. The proper way now to take this two-dimensional depiction of the shadow the molecule casts and convert it to a Fischer projection, that central carbon we don't write in. It is implied by the point at which these two lines cross. We don't draw in hashes and wedges, and we just put our substituents at the end of our lines. Substituents below the carbon on the vertical lines, substituents above the carbon on the horizontal lines. And so we can now convert from a perspective drawing into a Fischer projection and understand what stereochemical information is implied by that Fischer projection. From there, we can use Fischer projections to derive RNS absolute configuration. But before we do that, there are certain operations we're going to do moving groups around the ring. Some of them are allowed and some of them are forbidden. So we want to go over those allowed and forbidden operations before we use a Fischer projection to assign stereochemistry. So I'm going to start off with our forbidden operations. So let's start off with a Fischer projection of a hypothetical chiral carbon. And I have here 1, 2, 3, 4 different groups. So my first forbidden operation is the 90-degree rotation. So again, these are our forbidden operations, right? So the 90-degree rotation would just take this projection and turn it once. Our new representation would look like this. And the reason this is a forbidden operation is because if we convert this Fischer projection, these two Fischer projections, to perspective drawings or make models of them, we'll see that the relationship between these two depictions is that of enantiomers. So we cannot do 90-degree rotations right with our Fischer projections because that will result in a new molecule. The other forbidden operation, so again beginning from this same hypothetical Fischer projection, right, is if we do a flip, a pancake flip, right? So we're going to call this the flip operation. And what we see is we're now going to have our Fischer projection is going to create a mirror image when we do this flip. And again, if we make perspective drawings or if we make models of these two depictions, we're going to find that the relationship between the two of them is not that they're the same, but once again they are enantiomers. So we can't pancake flip or mirror image our Fischer projections. We create new molecules. We do, however, have two allowed operations. So my first allowed operation is the 180-degree rotation. So I'm going to take A and I'm going to rotate the whole thing 180 degrees. My new projection A, B, C, D, that puts B down here, C over here, D over here. If we create a perspective drawing or a model of this, we'll see that these two are the same, have the same configuration, same stereochemistry. And the other operation I'm allowed to do, right, is to swap three groups. So here now, starting from the same one, what I'm going to do this time is I'm going to take A, move it to B's position, take B, move it to C's position, and take C and move it over to A's position. And so now, my new depiction, so I'm going to call this the three-way shuffle. Right? So I'm taking A, putting it where B is, B putting it where C is, C putting it where A is, and my new Fischer projection would look like this. A, B, C, and D remains in the same place. And once again, if I make perspective drawings or models of each of these theoretical molecules, I'm going to see that I have made two things that are the same. So these are our allowed operations. Let's take a look at one quick example on how to use a Fischer projection to assign stereochemistry. So to start off, I'm just going to draw a Fischer projection of an organic molecule. So we'll put a methyl group there, a hydrogen there, an OH here. We'll put a couple of hydrogens here, and we'll put an aldehyde up there. By looking at this, there's only one chiral carbon in this molecule. Only one carbon has 4 different substituents attached. So now to set my stereochemistry, I have to look at the 4 different groups, first and foremost, and determine what their priorities are. So my lowest priority group here is going to be my hydrogen. My highest priority group at shell 1, carbon versus oxygen, oxygen wins. And if I compare this carbon group versus this group, I'm going to see that my group up here actually has higher priority, which puts the methyl priority 3. Right? So now, what I'd like to do is assign that stereochemistry. And if you remember, everything that's on a horizontal line is on a wedge. So really, I have to think of this here as being on a wedge. And now I need to do one of my 2 allowed operations to get that low priority group onto a hash, put it into a vertical position. So I'm just going to model, right, this chiral carbon, but without drawing in the groups, just putting in my priorities. So if I were to do that, I would have priority 1, priority 2, priority 3, priority 1, priority 2, priority 3, and priority 4. I'd like to do one of my operations to get priority 4 onto a vertical line, which would be a hash, which is where we need our lowest priority group to be. If I do my 180-degree rotation, I would just, right, it's going to put that low priority group back over here on this side, so I'd still be right on a wedge. That's not going to help me. However, if I do my 3-way shuffle, I can move my priority 4 group to where my priority 2 group is, my 2 group to where my 1 group is, my 1 group to where my 4 group is, and now I've got priority 4 on a hash, which is a vertical line. So let's go ahead, after doing our 3-way shuffle, let's go ahead and redraw this. And really, you can do any 3-way shuffle that will result in priority 4 group ending up where priority 2 or priority 3 is, as long as you get that priority 4 group onto a hash, which are our vertical lines. So after doing the shuffle, I have priority 4 on a vertical line where I need it. I have priority 3 where I left it. Priority 1 has now moved over to this side, and priority 2 is now here. The rest of the process is the same as what we have seen before. I'm going to go from highest priority to lowest priority and see which direction, clockwise or counterclockwise, I decrease priority. So going from 1 to, So going from 1 to 2 and 2 to 3, I am moving in a clockwise direction, which sets this stereocenter as R. So doing these types of tasks and developing the skills to do this requires practice. Lots of great practice questions regarding assigning stereochemistry in your POGIL worksheet. Lots of great practice in your Sorrel textbooks. I recommend you do all of the problems at the end of the chapter that discusses stereochemistry. This is going to be something that stays with us throughout Chem 201 and throughout Chem 202, being able to assign stereochemistry, right? So it's really important that you get lots of practice there. And the week 5 practice problems I handed out in conference, lots and lots and lots of challenging stereochemistry practice problems there for you as well. So I hope you found this video lecture informative. As always, if you have any questions, please bring them to conference, lecture, office hours, or make an appointment to see me. Thank you very much.